Hi, in this video we are going to continue our discussion of the singular value decomposition, focusing on how we develop this very interesting and powerful matrix decomposition. Let's begin with a discussion of matrices as sums of very low rank, rank 1 matrices. It is a fact that every matrix of rank R can be written as a sum of R rank 1 matrices. Just some examples shown here. This is a 3 by 4 matrix of full row rank, so it has a rank of 3. And we can write this matrix as a sum of a matrix that has 3 identical rows, rank 1, a matrix that has a row of zeros and 2 identical rows, another matrix of rank 1, and a matrix that has 2 zero rows and 1 non-zero, a rank 1 matrix. This is a 4 by 3 matrix where the first 2 columns are linearly independent, but the third column is a sum of the first 2. 2 linearly independent columns, a rank 2 matrix. We can write this as a sum of 2 matrices, each of which have 2 identical columns and 1 zero column. Each of these are rank 1. 3 rank 1 matrices to reconstruct a rank 3 matrix, 2 rank 1 matrices to reconstruct a rank 2 matrix. This sum is not unique. There are many different ways that we can write the same matrix as a sum of rank 1 matrices. I've just shown an example here. The same 3 by 3 rank 3 matrices. And I can write this as many different sums of rank 1 matrices. One is very similar to the one we looked at in the last case. I can start off by constructing a matrix that has identical rows looking just like the first. And then I can construct a matrix that has a first 0 row and a row that corrects the difference between this and the first row to give us the second row, and duplicate this so that I have the rank 1 matrix, and a third matrix that has 2 zero rows and a third row that corrects the deficiencies from adding up these two. I could also have simply taken 3 matrices that have 2 zero rows each and has the single row, either the first, the second, or the third, and this gives us this sum. I could take this same approach in a column-oriented fashion, constructing 3 matrices with 2 zero columns each, and a single non-zero column corresponding to the first, second, or third column. And there are more ways to do this. So we can always express our rank R matrix as a sum of rank 1 matrices, but there are many ways to do this. Rank matrices can always be expressed as what we refer to as outer products. We've seen inner products. Inner products are dot products. If we start with a column matrix V that is n by 1, and we multiply it with another column matrix of the same size, 1 by n, this gives us 1 by 1, or a scalar. This is the dot product we've seen before. If we simply flip the order of where we apply the transpose, we start with a n by 1 column matrix, column vector, and multiply this by a transpose of a vector of the same size, a 1 by n. The inner dimensions match, so we can apply this product. They cancel out, leaving us with an n by n square matrix. For the inner product, this only makes sense if the two vectors were of the same length, because we needed these inner dimensions to match. For an outer product, that isn't necessary. I can take a product of an m by 1 matrix and the transpose of an n by 1, or a 1 by n matrix, and this gives me an m by n matrix. Such products will always be rank 1. We can show some examples here from the breakdowns that we saw previously. This rank 1 matrix with 3 identical rows can be constructed by a single row vector corresponding to that row, multiplied by a column vector that has ones. This essentially creates a vector that has the same number of rows, where each of these is the same multiple of this single row. To construct a matrix that has a 0 row and 2 identical rows, again we start with that identical row as the right-hand piece. And for the left-hand piece, we have a 0 where we need to get a 0 row, and 1s where we want those identical rows. From a column-oriented perspective, we can think about constructing a column that corresponds to a column vector that corresponds to the column we're interested in, and then a row vector that scales that by 1, by 0, or by 1. Or we can also think about this in sort of these same contexts, this matrix that has 4 rows that are scalar multiples of each other can be constructed by a row vector that has the first, multiplied by the scaling factors that we need to reconstruct each of those rows. So we can see how these rank 1 matrices can be expressed as outer products of this form. Now, we've seen that every matrix of rank R can be written as a sum of R rank 1 matrices, which means it can be written as a sum of R outer products. Any m by n matrix of rank R can be written as a sum of R terms, an outer product of a vector that has m rows and 1 column, and a vector that has 1 row of n columns, this y transpose. Now, we also know that matrices of this form, any m-dimensional vector, can be written as linear combinations of a basis for Rm. And y, of course, can be written as a linear combinations of elements of a basis for Rn. We can also always choose such a basis. We can choose a basis for Rm, a basis for Rn that are orthonormal. So we could imagine constructing an orthonormal basis for Rm, an orthonormal basis for Rn. And this should allow us to write any of these xi's as linear combinations of these orthonormal basis vectors, and similarly for y with the second orthonormal basis set. These have to be different because in the general case, we're dealing with different parent spaces for these two vectors. This leads to an idea. This is not a. This is at this point is a declaration rather than a proof. But you can see, you might be able to see where the pieces are coming together. If we can write a matrix as a sum of these outer products, where each of these vectors can be written as a linear combination of orthonormal vectors. Perhaps we can write this matrix as a sum of outer products of specifically those orthonormal basis vectors. We will need to have some scaling factor in here to account for the fact that these vectors are not simply have non-1 scaling factors involved in here. Now, at this point, this is an idea. It turns out one to be true, that every matrix of rank R can be written as a linear combination of R outer products of orthonormal vectors with positive coefficients. And this is an extra little constraint that I've added here, that we actually are going to be able to do this only using positive scaling factors here. This idea is really at the heart of the singular value decomposition, and we're going to develop a more rigorous proof of this and how we can find this moving forward. All right. We can represent this same idea, this idea that we can write a matrix as a sum of outer products of orthonormal vectors with a scaling factor, by defining two square matrices, a matrix U, whose columns are an orthonormal basis for Rm, a matrix V, whose columns are an orthonormal basis for Rn. Just to be clear, what does this mean? This means that the dot product of Ui, Uj is 0 for all non-equal elements of this vector. The dot product of all of the columns is 0, and the same thing for the V's. Sorry, that should not be a transpose in that second position. And that in addition to that, the dot product of U with itself is equal to 1 for all I, and the same for V. Orthonormal bases. The columns all have a norm of 1 and are orthogonal to each other. We also define a diagonal matrix that is of the same size as A. This is important. The sizes are important. A is an M by N matrix. What we are going to devise is a M by M matrix U, an M by N matrix sigma, and an N by N matrix V. The inner dimensions here match, so that tells us that these products are well defined. They will disappear in taking the product, so these will disappear, leaving us with M by N, which is of the matrix of the same size. And this is the product that we're going to be evaluating. We can sort of think about where this comes from. The V transpose will have rows that correspond to these VI transpose elements. Multiplying a diagonal matrix by those scaling factors. Sorry, this should be well, we'll deal with this little subtlety in a moment. Multiplying by the scaling factors will add a sigma I times VI transpose. And then each of those rows, when we multiply the U with this appropriate structure here with the columns as the u vectors will give us rise to this, this sum. All right. This gives us a matrix decomposition, U sigma V transpose, where sigma is diagonal, U and V are orthogonal matrices with orthonormal columns. And this is what we refer to as the singular value decomposition. This is, again, at this point, still an idea. We can only do this using very special orthonormal bases. And what we're going to do over the next few slides is demonstrate where these orthonormal bases come from to convince ourselves that this is something we can actually make work. All right. So let's start with a goal of trying to do this. A little bit more than a goal of trying to do this. We're going to assume that we can do this, but that we don't know how to build U, sigma, and V transpose. We can do it, but we don't know how. The first thing that we're going to note is that the product of a matrix and its transpose is always symmetric. This we discussed in earlier units. So A transpose A will always give us a symmetric matrix, a matrix whose transpose is equal to itself. Right? We also know that symmetric matrices can always be diagonalized and diagonalized with orthonormal eigenvectors. This follows symmetric matrices, distinct eigenvalues are orthogonal to one another. We can always normalize those, and for eigenvalues that have eigenspace of dimension more than 1, that have a multiplicity of more than 1, we can always find an orthonormal basis for those, an orthonormal set of eigenvectors. Putting these two ideas together leads us to a very, very interesting result. We are simply going to plug in our target for the singular value decomposition into A in this A transpose A expression. When we propagate this transpose through this product, we reverse the order and apply the transpose to each element. V transpose V, sigma transpose, U transpose. Of course, sigma V transpose is just V. And this U transpose is then going to be multiplied by U. And since we have decided we want U and V to be orthogonal matrices, that is, they have orthonormal columns, this requires that U transpose U equals U transpose equals the identity matrix. The inverse of U is its transpose. This is a property of matrices with orthonormal columns, of orthogonal matrices. That means that this product EU transpose U disappears, and what we're left with is V sigma transpose sigma V transpose. This is a matrix multiplied by its transpose. It has to be square, it has to be symmetric. When we started out with sigma being a diagonal matrix, it has all 0 entries except on the diagonal. If we multiply this by its transpose will also be diagonal. And this is going to give us another diagonal matrix. Again, a property of just working with diagonal matrices. Note that sigma and sigma transpose are diagonal but not necessarily square. Their product is diagonal and square. What does that give us? Well, let's take a look at this. We have a orthogonal matrix V multiplied by a diagonal matrix, sigma transpose sigma, multiplied by the transpose or inverse of that orthogonal matrix. This looks exactly like the eigenvalue decomposition of this symmetric matrix. In fact, we can simply make an assignment of calling VQ and calling sigma transpose sigma lambda, and this gives us exactly this result. What does this tell us? It tells us that the singular vectors, the vectors of this V matrix, are simply the same as the eigenvectors of A transpose A. We know how to compute eigenvectors for a symmetric matrix. That tells us that we know how to compute the singular values to place into V. The eigenvalues of A transpose A, which again we know how to compute, are equal to the singular values squared. Again, this comes from this product. If we take the symmetric matrix, maybe I'll just expand on this briefly. If we take the product of a diagonal matrix with its transpose, this has all zeros on the diagonal. The transpose goes from also has those same sigmas on the diagonal. If we started with an M by N matrix, this will be an N by M matrix. This is going to give us an N by N, but what's going to happen? We multiply the first row by the first column. This gives us sigma 1 squared. All of the other products of the first row with anything other than the first column is going to give us zeros. The second row multiplied by the first column will give us a 0. The second row with the second column will give us sigma 2 squared, and the second row with all of the other columns will give us zeros. The product of this sigma transpose sigma is a symmetric matrix whose elements are the squares of whatever the elements of sigma were. So the eigenvalues of A transpose A, which we know how to evaluate, are the square root of the singular values that we want to put into sigma. This gives us part of the picture. We can compute singular vectors for V and eigenvalues, or singular values, sigma I, just by doing an eigenvalue decomposition on A transpose A. Now, let's dig into this a little bit more. Let's think specifically about the case where where lambdas are 0, where the eigenvalues are 0. Well, those singular vectors, right, satisfy the equation A transpose AX equals a 0. And that matches on to the null space of A. Vectors in the null space of A have AX equals 0. They satisfy the expression A transpose AX equals A transpose times 0, which is 0. So any vector that satisfies this equation is in the null space of A, also has to satisfy this equation, A transpose A, x equals lambda x, with lambda equals 0. The null space of A maps on to the eigenspace of A transpose A with eigenvalues of 0. A relationship between the null space of A, which we know how to calculate, and some of the singular values. Let's think about the singular values that have a non-zero lambda. These are vectors that satisfy this equation, A transpose A x equals lambda x, where lambda is not 0. If we simply make a statement that y equals ax, an assignment, we can rewrite this as A transpose y equals lambda x. Right? What is this? This is a linear system, and lambda x has a solution. If lambda x has a solution, it means that lambda times x has to be part of the column space of this matrix. Lambda x has to be an element of the column space of A transpose or of the row space of A. If lambda times x is in the row space of A, then x itself also does. The singular vectors that satisfy this non-zero eigenvalue are in the row space of A. It's kind of interesting. Now, not only have we found out a way to compute singular values and singular vectors by doing an eigenvalue decomposition of A transpose A, we can relate the answers to the null space and row space of the original matrix A. Okay. This is telling us something, again, about this special bases that are going to work to give us this eigenvalue, this singular value decomposition. Singular vectors vi with singular values of 0 are in the null space. Singular values with sigma not equal 0 are in the row space of A. Now, how did we get this? We got this by working with the product A transpose A, which we know to be a symmetric matrix. We can just flip this around. We could also have decided to kind of do the same analysis, but do everything instead working with A transpose A. Let's do the same thing. We plug this in, U sigma V transpose, propagate the transpose through. This gives us V transpose transpose, sigma transpose U transpose. V transpose transpose is V. V transpose times V is the identity matrix because V is orthonormal, so that piece cancels out. And what are we left with? We're left with U times sigma transpose times U transpose. Well, sigma transpose times, sigma times sigma transpose is also a diagonal matrix in exactly the same way as we discussed before. U is an orthonormal matrix. If we think about defining an S prime as A transpose A, this is a symmetric matrix also. It has an eigenvalue decomposition. We can write this as some Q prime, sigma prime, Q prime inverse. And by making exactly the same kind of equivalences, that Q here is U, sorry, not just inverse, we can do this with the transpose because we have a symmetric matrix. U transpose is Q transpose or Q inverse, and this lambda prime is this product here. If A was M by N, this product will be M by M. The previous one was N by N, and that's going to be the shape of this piece here. But all of the same logic works. We've just flipped things around. But now we're dealing with the other order. So the singular values ui that have sigma i's of 0 have to be in the null space of A transpose or the left null space of A. Right? We've really just changed the order of how we're dealing with everything. So now we're dealing with A transpose instead. The singular vectors ui with non-zero singular values will be in the row space of A transpose or the column space of A. This all follows exactly the same logic that we used to get our understanding of the vectors of V. All right. So where do we have now? We're at a place where we know that the singular values of Vi with sigma I equals 0 are part of the null space of A, and those with non-zero sigma I are in the row space of A. And similarly for U, the Ui with sigma I are in the left null space of A. The singular vectors with non-zero are in the column space of A, the row space of A transpose. That means that we can think about breaking up V into two pieces. A piece that has R vectors, where R is the rank, the dimension of the row space, that are an orthonormal basis for the row space of V, and a block of n minus R vectors that all are vectors that are a basis for the null space of Rm. And doing the same thing with our vectors U. We can break down U into a portion of R vectors, where R is the rank of A, that are a basis for the column space of A, and a remaining set of M minus R vectors that correspond to a basis for the null space of our matrix A. We have in A now this set of 4 fundamental subspaces of A contained in U and V. And there has to be a correspondence between these, where we match them up in the right way with the sigmas that match these. All right. Now, we've kind of done this in a way where we've looked at 2 separate eigenvalue decompositions, one for V, one for U. Are we really sure that these give us consistent results? Are we really sure that they map onto each other perfectly? Let's expand on this idea a little bit more. So we start with our idea here of A equals U sigma V transpose, with our general breakdown with V being a component from the row space, a component from the null space, and so on. And recall that V is an orthogonal matrix, meaning that its inverse equals to its transpose. What this means is that we can multiply both sides of this equation by the vector v. And when we do that, the v transpose v create the identity matrix that disappears, which allows us to write the expression equivalently in this form: A times V equals U times sigma. Think about what this now means. AV is A times this row space block and this null space block, which can be propagated in A times VR, A times Vn. But Vn contains only vectors that are in the null space. So A times those has to always give us 0. It gives us a matrix that looks like this. A times the columns of the row space, a matrix whose columns are the row space of A, and a block of all zeros. If we think about the right-hand side of this expression, U multiplied by this block matrix here, U will have the form, we multiply the first row by the first column, U C times sigma gives us plus ULN times 0 gives us this piece here, and the row times the second column gives us 0 plus 0, also gives a matrix with a block of non-zeros and a 0 block. Right? This equivalence can be expressed as this block matrix equivalence. The 0 equals 0 are kind of uninteresting, but we have this A times the row space vectors equals the column space vectors multiplied by sigma. Now, when we multiply on the right by a diagonal matrix, this has the effect of scaling the columns of this matrix. When we multiply a matrix by another matrix, we can think of this as multiplying the matrix by each row of that. And so this can be equally well written in this form. A times VI, sorry, each column of A times each VI is equal to sigma I times UI for each of the i's less than or equal to the rank. The null space piece and the left null space piece kind of are trivially equal to each other because they drop out as zeros. What this tells us is that although we kind of showed how you can take this A transpose A or AA transpose and get a symmetric result, that helps us understand the breakdown of the row space, null space, column space, and left null space. But it isn't actually necessary to find the vectors U. The singular vectors U can be derived directly from the singular vectors VI for all of the non-zero cases. Right? That is, if we know VI and we know sigma I, we can find UI. Right? So how does this all sort of sit together? This singular value decomposition, A equals U sigma V transpose, can be broken down. V is a orthogonal matrix, a matrix with orthonormal columns, where the first R columns are an orthonormal basis for the row space of A. The last n minus r columns are an orthonormal basis for the null space of A. The first r columns of U are an orthonormal basis for the column space of A. They're related to the set VR, the orthonormal basis for the row space by this relationship here, that ui equals 1 over sigma I a times vi, and the m minus r columns at the end of u are an orthonormal basis for A transpose, for the null space of A transpose, the left null space of A. That tells us that it's not just any orthonormal basis for VR. It's not just any orthonormal basis UC. It is a specific orthonormal basis for the row space that comes from the eigenvalues of A transpose A, and a special orthonormal basis for the column space of A that satisfies this relationship. The singular values are the square roots of the non-zero eigenvalues of this matrix, where we do have to take care that if we have multiplicities of more than one, we repeat them just as we do in a diagonalization of a matrix. In sort of conclusion, I want to discuss a little bit about the uniqueness of the singular value decomposition. We've shown that we can do this, essentially a procedure by which we can find a singular value decomposition. It starts with A transpose A. We find the eigenvalues. That allows us to define our singular value sigma by taking square roots. We can find the vectors of V by finding the eigenvectors associated with those eigenvalues. And we can find the columns of U by scaling those vectors in the right way and multiplying by A. Is it unique, or are there more than one U and V and sigma that can give us the same answer? Well, it's almost unique. One lack of uniqueness is that we're always actually allowed to rearrange the order of the singular values in this diagonal matrix, just as we are in the eigenvalue decomposition. We can move around where the eigenvalues in the diagonal matrix are, as long as we move around the columns of V and U to match that. Right? However, we avoid that lack of uniqueness by stating a convention that we will always, for the singular value decomposition, order them by decreasing magnitude. That is, the first one is the biggest, the second one has to be less than or equal to that, and so on. Right? We have, so that handles this piece. If any of the singular values are repeated, that is, they have a multiplicity of more than one, then we have some ambiguity in defining the corresponding VIs, the corresponding row space vectors. We can choose any orthonormal basis for that eigenspace. Right? We find the special solutions and orthonormalize them with Gram-Schmidt, for example. And that is a fine choice. Right? Once we've made that decision of which orthonormal basis we use for VI, that will determine what the corresponding UIs have to be by this scaling relationship. Right? We can't independently find these doing a different eigenvalue analysis on the AA transpose. We need to make sure that we have a consistent choice. So this is one bit of non-uniqueness that only applies if we have repeated singular values. Another piece of ununiqueness is kind of related. If we have repeated singular values equal to 0, in other words, if the nullity of A is greater than 1, the null space of A has a dimension of more than 1, or if the null space of A transpose has a dimension of more than 1, then we have some ambiguity in how we choose either the null space or left null space basis. If the null space has a dimension of more than 1, any orthonormal basis for that null space works as our set of vectors Vn. If the left null space has a dimension more than 1, any orthonormal basis can be chosen for the corresponding entries. Right? But with that caveat that if we have larger than one dimension null space or left null space, or singular values that are repeated, there's a little bit of ambiguity. Otherwise, the singular value decomposition is in fact unique. In this video, we went through quite a sort of a conceptual discussion of what the singular value decomposition is, where does it come from as sum of rank 1 matrices, how we can relate it to the eigenvalue decomposition of A transpose A, and so on. In the next video, we will discuss how we can actually use the SVD to solve a number of very interesting problems, many of which involve data matrices, but also some applications to systems of equations as well. Thank you, and goodbye.